Oh, Calc AB. This video is actually for people who maybe missed the class on Wednesday. Since I have to be gone Thursday, Friday, and then again on Monday, I thought probably better to drop a video in about integration by parts, even though we talked about it in class. If you were in class and wanted to watch this video because you're like, hey, maybe I could use a refresher on that, by all means. It's meant to be a guide for you guys. Integration by parts is a integration technique that's quite powerful in a lot of instances where it might look like the initial integrand doesn't actually have an antiderivative. And so what we're going to do here today is we're going to take a look at integration by parts, and I'm going to put the basic plan up first for integration by parts, and then we'll kind of talk it through. Integration by parts centers around one particular type of integral, and the integral fits a pattern, the integral of u dv. And so there's a function u in there, and there's a differential for a different function, v. Now, they may be related to one another, they may not be related to one another. But the point is, we're looking at this, and it's not a simple u substitution. It's not a simple rewrite of the integrand. It needs something a little bit more powerful. And so the integration by parts is powerful. It's also can be quite complicated and convoluted, especially because you might have to apply this more than one time. And so it's not a go-to like immediately in your thinking when you're doing an integral strategically. What do I want to start with on the integral? This would not be early on in my list of things that I would like to see you try. But if you recognize the u times v pattern, then what you can do is that integral will be equal to u times v minus the integral of v du. Oops, that's a u. Sorry. Okay, and this this really comes from the product rule for derivatives. And so when you get this, if you're like, where'd that come from? It came from the product rule. Oh, goodness. Let me undo that. There we go. We'll just leave it in my ugly chicken scratch there. Okay. And so what I mean is, if you think about the product rule, okay, bring up a pen here would be handy. The derivative with respect to x of f of x times g of x. Okay. Well, you know the product rule. That is f prime of x, g of x, plus f of x, g prime of x. Right? And then if we were to say, oh, well, let's anti-derive this. Okay. Well, we know what the second fundamental theorem of calculus would tell us about it. So we'll do this, and we'll do this. Right? And notice what that gives you. On the left-hand side, it gives us f of x times g of x. And on the right-hand side, notice what it gives us. It gives us the integral of f prime of x gx dx plus the integral of f of x g prime of x dx. And all we have to do is move that first one over. And we get that, oh, look, f of x g of x minus the integral of f prime of x g of x dx is equal to the integral of f of x g prime of x dx. And you're probably looking at that going, well, how is that the same thing? Well, think of f of x is the function u, and g of x is the function v. And then rewrite it. Well, that would be u times v minus the integral. Well, g of x is in there, so v, and f prime of x is in there. Well, that's du. And over here, we have f of x, which is u, and g prime of x, which is dv. So really it is. It's just the product rule, guys. And so when we recognize that we're going to use this pattern, we're really thinking, okay, this was something that came out of a product rule. Okay, so let's put the product rule back together. When we do that, it allows us to then integrate some functions that previously we wouldn't have been able to do at all. So that's a little bit of what it is, where it came from. Let me show you how it works kind of in practice. Okay, so let's say we were trying to take an integral here and we had x times sine of x dx. That's a real problem given the techniques that we know at this point, because we don't know how to do x times a function. There is no product rule for anti-deriving. Okay. There's for derivatives, which is where this comes from, but we don't have one to anti-derive this. So we're going to then say, well, what other techniques do we know? U sub, well, won't work because there's no way to sub out the sine of x, because we would need cosine of x in there, and we don't have that. Can we sub out, x? Well, you could, but then you'd still have, u times sine of u du, and that doesn't get you very far. So integration by parts comes along and says, well, here's what you do. Now, usually what we try to do in integration parts is let dv be the part of the integrand that's more complicated. But you have to know how to anti-derive it, and that's key. So if this is my dv, do I know how to integrate sine of x dx? dv will be sine of x dx. And the answer is yes, of course. If we integrate both sides, well, the integral of dv, of course, is v. And how about the integral of sine of x? Yeah, you know that one. It's negative cosine of x. So already we're off to a good start. I have a dv that I do know how to anti-derive. The other part of this is, okay, sorry about dv there, is that means this first function has to be u. Okay, so if u is equal to x, du is equal to dx, and that's going to make life pretty easy, because you can see what will happen if I put the pattern up there on the screen. I'm going to rewrite this as u times v, so x times negative cosine of x, minus the integral of v, which I'll keep it negative cosine x right now, du, which is dx. And so that factor of x that was in the original integrand that was making it sort of impossible for me to do is gone. And that's really the key. Let me simplify this a little bit. And we do know how to integrate cosine of x dx. That's just sine of x. And then we'll put our plus c at the end there. And so that's what integration by parts allows you to do. Take an integrand that previously we probably would have had some difficulty with, and say, oh, but if I make a smart choice of what's u and what's dv, I can get this integral to be something that I really would be able to do. And hopefully remove that term that's causing the problem. Let's try it again. Let's try it again with another one. This is a pretty common one. Let's do t squared e to the t dt. Now, in this one, I actually could choose either one of those to be my v and either one to be my u. I know how to anti-derive both. I know how to derive both. So when we're sort of equivalent, we want to think to ourselves, which one of these gets simpler as I take the derivative of it. Well, e to the t, if I take the derivative of it, stays e to the t. It doesn't really get simpler. Okay? But t squared, if I derive that, becomes linear, right? It becomes 2t. So that does tell me that a smart choice here is probably to make this u, okay? Because that will get simpler as I derive it. And then it also works because of the two functions, which one's more complicated? Well, e to the t is a little more complicated than t squared because of the exponential. And I do know how to antiderive e to the t. Everybody loves e to the t, dt, because the antiderivative of e to the t is just e to the t. E to the t is everybody's favorite function when it comes to deriving and antideriving because it doesn't change. Okay. More importantly here, if u was t squared, du is 2t dt. So I can take my original integral and rewrite it as u times v. So t squared e to the t minus the integral of v du. So 2t e to the t dt. But see, I'm still stuck because I have a t e to the t here. Okay. Let me rewrite this a little bit. T squared e to the t minus 2 integral t e to the t dt. That's a t there. So how are we going to do this one? Oh, guess what? We're going to use integration by parts again. So we're going to have multiple iterations of integration by parts. That happens a lot in the integration by parts. There's my u, there's my dv. This time, well, v is still going to be e to the t, but now look, du is just dt because the derivative of t is just dt. So I still have my t squared e to the t minus 2, but now it's going to be multiplied by our next iteration of integration by parts. So I've got t e to the t, that's u times v for this one, minus the integral of v du, which is e to the t dt. And now, do you know how to integrate the last standing integral? Yes, e to the t dt is going to just be e to the t. So we'll have our t squared e to the t minus 2 times t e to the t minus the antiderivative e to the t, which is e to the t. At this point, you could clean this thing up if you wanted. You don't have to, since there is the nice common factor of e to the t in there. Well, we could factor that out, but it doesn't really save us any time. So, all right. Integration by parts also helps us with some functions that maybe we've never integrated before. For example, we have never taken this integral. Even though we've done lots of integrals, and this one looks fairly simple, it's actually quite complicated because there's no elementary way to do it. You have to be able to use integration by parts for the integral of natural log of x dx. Okay. But you might be looking and go, whoa, wait a minute. What's going to be u? What's going to be dv in this one? Well, in this case, we're going to go with the rule of thumb that says let u be a function in my integral that gets simpler as I take its antiderivative, or as I take its derivative. Because if u is equal to natural log of x, what is du then? Remember the antiderivative? Or sorry, the derivative of natural log of x? I keep saying antiderivative. I don't mean to. It's 1 over x dx. And that is a little bit simpler than natural log of x. And that means this dx is dv. So if try that again. If dv is dx slap some integrals in here. What does v equal? The integral of x of 1 dx is just x. So my integral of natural log of x dx, when I break it with integration by parts, is v times u, x times natural log of x, minus the integral of v du. Well, that's 1 over x times x dx. And look at that. 1 over x times x, that's just the integral of 1, which is just x. And this is the reason we had never done the integral of natural log of x before, because you had to know integration by parts to be able to do it. All right. Integration by parts, that is the basic procedure for it. Now, if you are dealing with a definite integral, okay, meaning you have limits on your integral, I think what you're going to see is that those limits just continue to follow along with the antiderivative, so it's not overly complicated. If you look on page 527 in the text, you'll see an example of how they did arctan integral, and they used it with the limits 0 to 1, and so they show you how to follow the limits through on an integration by parts. Okay, guys, that's it for integration by parts. Hopefully that helps you guys with that if you were gone on Wednesday when we went over it. Have a great rest of your week, guys. I'm sorry I can't be there for Thursday, Friday, and Monday. I'll be back on Tuesday, and we'll continue hitting our integration techniques as we go forward.